We are now going to be looking at magnetism. We're going to take the next two chapters, chapters 21 and 22, to investigate magnetism. And we're going to find out that right out of the gate, this is kind of the big theme of the entire chapter 21 and 22, but there's a fundamental link between electricity and magnetism. And most importantly, and I'm going to highlight this, the most important thing to remember is that all magnetic forces and fields are produced by moving electric charges. In order to get a magnetic field, in order to get something to become magnetic, you have to have a moving electric charge. That is the main key, main idea. So we're going to start out by just talking about a little history of magnets, okay? And generally, magnets are made out of steel or cobalt or generally another hard iron ore, that kind of thing. And they have the ability to exert strong attractive forces on certain objects. Now, the difference between magnetism and electricity, whereas electric charges, electrically charged objects, have the ability to attract or repel all objects, magnets only work on certain ones. And it was the Greeks that actually discovered this before, back in the early 600 BC or around there. And they knew about it because they had a naturally occurring magnet called lodestone that they found in the rocks. Okay, and I will show you one of these when you come into class. Okay, so magnetite lodestone is this naturally occurring magnet, and we were able to attract other things with it, but not everything. Okay, now we then go forward, okay, just a little bit, because the Greeks realized that you could have this attraction, this repulsion, that kind of thing, but that's kind of all they knew about it. They knew it was kind of neat, hey, look, it's fun to play with, but they didn't really use it for anything. Well, it turns out that if you take a bar magnet and you suspend it, so you hang it from a wire, and you suspend that bar magnet, one end will always point towards the north, and one end will always point towards the south. And so once they discovered that, that's how they named the two sides of the magnet. What they named is the poles. And so the end that points north is known as the north pole of your magnet. The end that points south is known as the south pole of your magnet. Okay? And so that's how we named those poles. Now, William Gilbert in 1600 AD went further and said, hey, okay, that's kind of neat. But since we now know that magnets only exert forces on other magnetic objects, on certain things, and if we suspend a magnet, one end always points north, one end always points south, there must be a giant magnet inside the Earth itself. William Gilbert came to the conclusion that if this is the Earth, and I'm going to do a bad picture right now, and then I'll just show you a better one here in a second. But, you know, here's Florida and North South America, but you get the idea. Over here's Africa, Australia, Hawaii, but you get the idea. Okay? William Gilbert supposed that there was a giant magnet in there as well. Okay, so the Earth has its own magnetic field. And this is what causes any suspended magnet to rotate. Okay? So here's a better picture of it. Okay, the one that I stole. Okay, what's kind of neat about this is we actually have a suspended magnet. Well, I'll let you play with this when we get into class as well. I'll hold it up. But if you've ever seen one of these before, a compass, all this is a suspended magnet. I can't really get it so you can see that it does wobble, but I can't hold it so you can see it rotate. But there's one end that always points north, one end that always points south. Okay, but it turns out that the Earth's magnetic poles are not the same as the geographic poles. And this is because the magnetic field is off by about 1,800 kilometers, or if you can see by this picture, about 11.5 degrees. Remember that the Earth itself is tilted 23 degrees. Yeah, 23 degrees, trying to channel my inner Earth science. Okay, the magnetic pole is only tilted about 11.5 degrees. Okay, so your compass, your magnet is not pointed true north. Okay, but again, not anything that's really crucial about that. Now, the other thing that we came up with this is they found out that some things were natural magnets and had these magnetic abilities. Other things could be attractive, but weren't always necessarily magnetic. Okay? Well, if you take a piece of unmagnetized iron, and I'll demonstrate this for you tomorrow in class, something I can't pick up paper clips or whether it's not magnetic, but I bring it close to another magnet, it will suddenly become magnetic. Okay? And so since it's only temporary, okay? And only when it's close, we call it magnetism by induction. So this is called a temporary magnet. And it becomes temporary magnetic by induction, because this will work even if there's no, even if it's not touching, okay? We can actually show this too, is that any fixed iron object that you put in the earth, so I'm gonna come back to this picture. If I put an object, let's say I stick a metal pole right here, like this, okay? What will happen is that metal pole will eventually become magnetic. And what's kind of neat about this, okay, now, something I left off that I have to go back and talk about here. Remember how we said that if you suspend a magnet, oh, green's not gonna work there. Let me get rid of this. Let's go with orange. If I suspend a magnet, one end always points north and one end points south. And I'm gonna zoom this in just a touch so make it a little easier to see. So we have one end that points north and one end that points south. Okay? But remember, opposites attract. And so when the north pole of our magnet points north, it's actually attracted to the south magnetic pole of the earth. The south pole of your magnet is pointing to the south, so it's actually attracted to the north pole of the Earth's magnetic field. So the southern magnetic pole of the Earth is in the geographic north. Now that sounds weird, but all you gotta remember is, hey, wait, in my magnet, north points north, but opposites attract. So the northern geographic is actually the southern magnetic. So if I were to put this iron post in here like this, what would end up happening is that this bottom part would become a north pole because it's attracted to the south, and the top part would become a south pole of any fixed iron object that I put in there. And so the Earth's magnetic field, although it is extremely relatively weak, will cause other things to become magnetic. So let me scroll back up to this. Now, as we said, there are permanent and there are temporary magnets. The difference being that if something always has its magnetic field, so it stays magnetic, it retains it, whether or not it's near another magnet or not, that is what it becomes a permanent magnet. So it retains its magnetic field. Okay. Where if it's temporary, it's only magnetic when it's close to another magnet. Now, the other thing I want to tell you here too is we're not going to go very in-depth into magnetism. The New York State Regents doesn't require us to do a lot of in-depth study on magnetism. It's actually extremely complicated. You can talk about diamagnetic, paramagnetic, and all that other stuff. We're just going to scratch the surface so you have a base understanding of it. So if this gets a little complicated, a little crazy, don't worry. We'll simplify it out so you just see what you have to know. Okay? Now, we have talked about how there's electric fields. We've talked about how there's gravitational fields. Well, there's also magnetic fields. And so just like electric charges, remember with electric charges, we had the positive charge here. We said, hey, there's an electric field around it that surrounds it. And it's the interaction of that electric field that actually exerts those forces. The same can be said about the magnet. If here's my magnet, there's my north, there's my south. This has a field of force around it as well. And I'm going to do my cruddy picture to start, and then I'll show you the better one that I copied here in a second. But there's a magnetic field around it that surrounds it. And we will get an opportunity, if we are in class and we can do lab, you will actually get to play with bar magnets and iron filings to showcase these magnetic fields. Now, there are properties to these magnetic fields that you have to know. First off, and we'll base it off of this much better diagram. First, that the north pole of a compass placed on there will always be tangent to the magnetic field line. So if I put a compass right here, its north pole will be tangent to the field line at that point. So the compass will point there. If I go here, the compass will point tangent to that field line. Okay? So these field lines if you put a compass there, it's always going to show you the direction. And it's always tangent to that field line at any point. The second one is that the concentration of lines gives you the strength of the magnetic field. And so I'll circle this right here. These lines are close together. That's going to equal a strong magnetic field. Strong. Okay? Out here, and I'll go out on this side, out here the lines are further apart. And that's going to be a weaker, I'm not going to say weak necessarily, but a weaker magnetic field. Okay? Now, the last little tidbit is this, okay? And this is not showcased in this diagram, but I'm going to add to it. These magnetic field lines are actually all closed loops. What you're seeing in this diagram is them coming out of a north and coming back into a south. But what you're not seeing is on the inside, these lines actually connect. And on the inside, they go south to north. They are all closed loops. Oops. Bring that down here. And go straight across. I seem to have forgotten one. You get the idea. But inside the magnet, they go south to north. Outside of the magnet, they go north to south, always. Okay, by our definition of how we're going to define our magnetic field lines. And very, very important, these lines can never cross one another. Okay, so let me highlight that. These lines of force can never cross one another. Okay. So tomorrow we're going to go through a little bit more in depth here. We'll draw a couple more diagrams. I'll actually pass around some stuff so you can actually see it and work it. We'll try and do our lab with this if we have time. We'll go from there. But this is a good place to end with the intro to magnetism. So everybody have a great night. We'll see you later. Bye.